graph, whereas we are going to study about minimum spanning tree. It is a subset of graph which has all the vertices covered with the minimum possible number of edges. It doesn't have any cycles and it cannot be disconnected. Okay. So for minimum spanning tree, is consider a graph that is non-directed graph, unordered graph, that is A and B and C. Each elements are disconnected to one another. So minimum spanning tree means there's only minimum number of edge vertices, that is A, B and C. Everyone is connected, but there is no loop. So here A, C and B, C, A, B, C, A. So what happens is, so extra this edges will be removed. Why? Because it's cost another round of things. So here the maximum number of spanning tree will be in hence the order of n power n minus 2. Here n is the number of element, n is 1, 2 and 3, n power n minus 2, that is 3 power 3 minus 2, then that is equal to 3, that is 3 spanning tree. For a graph it has n power n minus 2 spanning trees. In this graph G we have 3 spanning trees, 1, 2 and 3. General properties of spanning tree. We now understand that one graph can have more than one spanning tree. For example, a connected graph G have more than one spanning tree. All possible spanning tree of graph G have the same number of edges and vertices. The spanning tree does not have any cycle, that is loop. So here this is a tree which have a loop A B C A B C, but in this there is no loop. Okay, so at the same number of edges. Here just say same number of edges in sense. In this graph also there is 3 edges, in this also there is 3 edges, 3 edges, 3 edges. This is what happens. All the vertex changes, only the arcs changes. That's possible, the connection also changes. Okay. A connect graph more than one spanning tree. A spanning tree has always more than one spanning tree. That is, in here A, B, C is a connected graph, have 3 power 3 minus 2, that is 3 power 1, that is equal to 3. 3 spanning trees, minimum spanning trees, 1, 2 and 3. Okay. Next, mathematical properties of spanning tree. A spanning tree has n minus 1 edges, where n is the number of edges, that is vertices, number of vertices. The spanning tree has n minus 1 edges. Okay, here number of elements is 3, 1, 2 and 3. What are the edges? In this non-spanning tree there is 3 edges. Now here 2 edges, 2 edges, 2 edges. That's what I here say. That is, from a complete graph, by removing, spanning tree has n minus 1 edges, whereas where n is the number of nodes. Okay, n minus 1 edges. That is, if there is 3 elements, then we can have only 2 spanning tree, 2 vertices. Okay, 2 edges. A complete graph has a maximum of n power n minus 1 number of spanning tree. Okay, I'll just write that. Okay, common application of spanning tree: civil network planning, computer network, a routing protocol, cluster analysis. So common applications means civil network planning. Civil network planning in the sense the civil network planning doesn't have any redundancy. Okay, so for example, if you have a electricity board, each house have only one electricity connection, right? That is what is civil network application. Computer network routing protocol, the same thing also. So if you are applying for broadband, if there is only one broadband for you, so you can use only one. There is only one connection. So from that you can use, there is no redundancy. Okay. So cluster analysis, in the cluster itself, the connection will be between one person has only one connection. There is no redundancy. Okay. So there is some algorithms, minimum tree spanning algorithms, Kruskal's algorithms, and frames algorithm. Okay. Kruskal's spanning algorithm. So this algorithm is considered that each element will be considered as a forest. Okay, as an independent tree. Its graph is considered as a forest, but each nodes will be considered as a single individual tree. And if you want to travel from one place to another, we don't have any loop. anything else, we must find the minimum shortest path. Okay, so actually here there is a graph, non-directional graph. 7 3 8, these are the numbers which gives the value of the edge, that is, it shows the edges traveling time, that's traversal. Okay, so let's start the example for removing our loops and parallel edges. So here one loop is here in the C, there is a loop. C itself, there is a loop, it's calling itself, say an edge of 1. There is no need of using this. You don't want to come start C and then end in C. There is no need of this. Okay. Then this is the parallel edges. That's A to B. There is a parallel edges 6 and 9. So 9 is the highest edges. So it has a value of 9, and another edge has a value of 6. So 6 is very low. So we remove the 9. Okay. So remove 1 and 9. Next. In case of parallel, keep the one which has the least cost associated and remove all others. Okay. If there is parallel, we have to remove the highest element and we have to keep it the lowest element, lowest cost. Okay, here arrange all these in incremental order of weightage, that is BD 2 and DT 2, AC 3, CD 3, CB 4. Like this we have to arrange it in ascending order. So add the edges which has the least weightage, add the edges which has the least weightages. Okay, now it has the least weightage, and when combining two two, it's very high, so we have to discard it. That's what our meaning is. Okay, next cost, find the cost of these things, parallel edges AB, AC and CD, we add them again. Okay, next cost of table is for we observe that all it will create in the circuits. So there is edge C to D and D to C. So with the cost of 5, we can traverse 1, 2 and 3, and by C and B we have a cost of 4. So we have to discard this. We have to keep 3, CD and DD. Okay, so that happens here. Okay, so now BC lowest cost, CD is the lowest cost, and BD is the lowest cost, and BT is also lowest cost. So here these two has an edges, that is 7 and 8. So that's 7 cost very low. So the cost of this S and A is very low, that is 7, and S and C is 8. So we discard S to C and take S to A, C, D, B and T. So we'll find the final result is this is the minimum spanning tree, that is each edges will be connected at least once with minimum weightage, minimum cost, with the cost of very minimum. So consider S and A cost very high, S and C is very high, so we are using 7, discarding the 8. So 7, 8, 3, 2, 5. So in the first example I say, so the minimum S to A is 7, so A to C is 3, so discard 8. So here it's 4. In the cost we can able to maintain 3 and 2, we can use it 5 rather than 4 and 6. So yes, A, C, D 3, B and then T. C it's very high, 5, so we just discard. So 7, 3, 3, 2 and 2, 4, 7 and 10, 17, just 17 cars. Okay,